Yes, so in this session, we are going to discuss out the fitting of exponential curve by the method of least squares. As we have seen in our previous sessions of method of least squares, we have done the best fitted, we have obtained the best fitted straight line to a bivariate data or corresponding to a scatter diagram coming out of a bivariate data. And then we have done the fitting of a parabola curve corresponding to a bivariate data. Now we are moving on to our next structure of the curve, that is the exponential curve. How we can fit, or what will be the expression for fitting a exponential curve corresponding to a scatter diagram coming out of a bivariate data. Right, whatever the methods we have utilized in the previous two sessions, that is the method of least squares. Same method we are going to utilize over here, that is the method of least squares. And the methodology, the steps to obtain the best fitted curve is same as we had on the same method, that is the method of least squares. So as we have seen, as we are, rather you can say, as we are dealing with the bivariate data, it contains two types of variables. One is the independent variable and another is the dependent variable. So I have taken the independent variable as x1, x2, x3, xn. If your data, if your statistical data contains n number of entries, and the dependent variable is y1, y2. Correspondingly, it goes up to yn. Now comes to the structure of the curve. As we are taking the case of exponential curve, fitting of an exponential curve, so correspondingly, the structure of fx or structure of curve will be exponential, that is a b to the power x, where a, b are the constant quantities. Now again, as the method goes on, our target is to find the value of small a and b, the constant, the unknown part, a and b. If we get the value of a and b, then the curve will be y equals to, or fx equals to a b to the power x. That will be the best fitted exponential curve corresponding to the bivariate data. So let us move on. As we have done for the utilizing the least square method, that first we are going to take on the distances from each and every point of the bivariate data to the best fitted curve, or to the best fitted curve equation we have taken. After taking that distance, we are going to square up the distance. Then sum of the squares of that distance will be minimized. So let us move on step by step. First, I'm going to write the distance, or rather, before moving on to the distance, yes, let us write the distance and then I can reform the curve. So the distance, I can take it as small di equals to yi minus ab to the power xi, ab to the power xi. Now, I'm taking this distance at first in a bit simpler form instead of taking the this power form, to overcome the difficulty in the power form, because while taking the derivative, it will be difficult for us to take on this form. So let us take logarithm on both sides of this distance equation, so that it will be easier to evaluate furthermore, or it will be easier to differentiate while minimizing the sum of the squares of distances. So taking log on both sides, taking log on both sides, we will be having the equation as log di equals to logarithm of yi minus log a plus xi log b. Now let us simplify it a little bit furthermore. Log di, I am substituting by giving some substitutions rather. So log di, I am substituting it as capital Di. Then log yi as capital Yi minus log a as capital A plus small xi log b as capital B. So this substitution we have made. Now you can see we have got a simpler structure as compared to the previous one, which is we are getting in terms of some powers. Now, if now we are going to minimize the squares of this di, some of the squares of this di. So let us take some of the squares of di, that is summation di square. Let us denote capital D as sum of all di squares. Obviously, I varying from 1 to n, sum of all di squares. So this will take the form summation I varying from 1 to n. Di squared means yi minus a plus xib whole square, right? Now we are going to minimize this capital D, as capital D is what? Sum of the squares of the distances of the curve taken from the given bivariate points in the data, right? Now to minimize, our next task is to minimize D. So let us move on to this portion of the whiteboard. Now I am going to minimize capital D. Minimize capital D. So to minimize capital D, we need to take, since a capital A and B are the unknown parts, we need to take the derivatives with respect to A as well as with respect to B. So let us take that del A of capital D. What it gives? Differentiating with respect to A, it will be getting, we will be getting it as twice summation over I yi minus a plus xib, and since the coefficient of a is only -1, so it will come out as -1, and this will be equals to 0. So del A of capital D, equating it to 0, we will be getting it as summation yi minus summation A, summation over I obviously, minus B summation xi equals to 0, or else after simplifying we will be getting as summation over I equals to summation of all A's taking I varying from 1 to n. So n times of A means it becomes NA, or you can write it as AN plus B summation xi. So this is one of the normal equation to get the best fitted curve or to obtain the value of A and B. Now next is we have differentiated D with respect to A. Now we are differentiating D with respect to B. So let us take the another differentiation with another unknown part, that is B. Del B of capital D gives us 2 times of summation over I, as similar to the previous one, yi minus a plus xib, and since the coefficient of b is minus xi, so minus xi will come out and that will be equated to 0. So now after simplifying, we will be getting it as summation xi capital yi obviously over I minus a summation xi minus b summation xi square equated to 0. Or we can write finally this as summation xi capital yi equals to a summation xi plus b summation xi square. So this is the next another normal equation we have got. Now solving these two normal equation for the values, we can solve these two normal equation for the values of capital A and B, which are the unknown parts. Now if you get the value of A and B, our target is actually we have taken the curve in the form of fx equals to small a into b to the power x, and we have taken the substitution capital A as log of a, log of small a, and b as log of small b. So from these two equations we will be getting the value of a and we will be getting the value of b. Then small a will be obtained as taking anti-log of capital A. Similarly, small b will be obtained as taking anti-log of capital B. So likewise, we will be getting small a and small b, and the corresponding curve will be obtained fx equals to a b to the power x. So this is the way how the exponential curve is fitted to a given bivariate data or to a given scatter diagram which is coming out of a bivariate data using the method of least squares. In our next session, we will be taking the another curve, that is the geometrical curve, to fit it to a bivariate data. Right? That's all for this session.